Yeah, good afternoon. This is David Eastwood, Geotech Engineering and Testing. I hope everybody can hear me. If not, send me something in the chat, something that tells me if you're hearing me or not. Um, yeah, it sounds good. So I get response. Everything sounds good. So we're gonna get started here. It's about 1 o'clock right now. People are coming in. Today, what we're going to be talking about is pre and post construction evaluation at swimming pools in Houston. This is really about gunite that we're using on our pools in Houston area and some of the problems with the gunite that we're running into. Uh, this is for 2 projects in the Houston area. We got about 150 people RSVP on this thing, bunch of civil engineers, you got some structural engineers, you got some pool people, architects. So it's just a lot of people. This is my contact information. My email is de@geotecheng.com. Telephone number 713-699-4000. We're gonna go ahead and put this on YouTube. You can go out and watch it anytime you want. We got about 35 programs on YouTube that you can go watch and shoot us an email, or we'll send you a PDH if you watch them. So there's a lot of interesting stuff on our YouTube channel that you can go watch and get PDH. Geotech is located in Houston. We've been around 40 years this year. We do geotechnical, environmental materials, and geoforensic engineering. We got about 60, 65 people. We work all over Texas, Louisiana, Oklahoma, New Mexico, and Arizona. We have our own rigs, labs, we're accredited. So we're ready to go. If you have questions, please type them in the chat or Q&A. I try to answer them as we go through. Let's see, you got some, okay, nothing. Project locations, we got 2 projects. These projects are rec centers for subdivisions. One in Willis, one in near Texas City in Galveston County. And they build these big pools out there in recreational centers, and you know, some of the gunites are not good. So we're going to be talking about the site 1. This is the Willis site. We did the initial geotechnical for the pool and the rec center. We did recommendations for pool foundations. We reviewed the plans and specifications we did a quality control for it. So we reviewed the plans and specs. We did site visit, density testing, steel placement, gunite testing here. There was no chemical injection on this site. But typically, you know, like if your soils are expansive, then we do chemical injection and monitoring. The project is out there near Conroe. Here's some pictures of the site. It's a nice rec center, but you know, see cracks here, cracks in it, cracks right there. So the site's got the pool has many cracks in it, in the gunite. You can see them through the plaster. Here are the cracks. So they had to empty the pool to check out the place, and they had to put these little holes in it to relieve the hydrostatic pressure at the bottom of the pool to reduce potential for uplift. Geotechnical study, project site 1. We did the geotechnical study for this thing, for this rec center and the pool. We checked the site conditions. We did the plan of borings. We developed soil stratigraphy, groundwater table, whether or not soils are expansive. We did lateral pressures for the pool, OSHA soil classifications for excavations, did laboratory testing, skin friction along the pool, recommendation compressive and uplift capacity of drill piers if they used it, dewatering recommendations, PVR at the deep end and shallow end. That's very important. Edge moisture distance, how far moisture from the pool extends out that affects shrink swell problems, depth of movement active zone, depth of root fiber, are there trees near the pool, tree trunks, diameter, sizes, recommendations on uplift capacities of the pool, recommendation on whether the soils can be used as fill that are excavated, consideration and maintenance programs, trees and drainage. So these are some of the stuff that we looked at on this thing. These are the truck mounted rigs. So initially we go out there and do borings next to the trees, get root fibers, and root fibers from trees tell us a lot about depth of movement active zone. If the soils are expansive, that's the zone at which soils experiences shrink and swell. Again, these are truck mounted rigs. The typical soils that come out, we extrude from the site. If the soils are sandy, that's a split spoon sampler. We test the soils for how strong it is based on the SPT values, standard penetration test. We measure the water level with the tape measure with the weight at the end of it. We throw it in the hole. When it hits water, it tells us the goes plumb. We just know the water depth. And it's not very accurate because water level changes all the time. So if I go out there and check the water level right now, it's going to be deep. If they're going to build a pool in February, water table is going to be shallow. So it's just an indication. It's not very accurate. Lab testing, we do the standard lab testing. I'll just talk about them for a minute. It's a liquid limit test. In this test, we take the soil sample. We add a lot of water to it, but it becomes a liquid. We get a spatula, put a piece of it here and spread it, and then cut a groove through it and turn the handle 20 to 30 times. Once the groove comes together, we get a sample of the soil and weigh it and get wet weight of the soil, and we put it in the oven and dry it up and find out when we dry it up is how much water is in the soil for it to behave liquid. Then we also run plastic limit tests. In this test, we take the soil sample and we roll it to 1/8 of an inch and try to find out how much moisture in the soil so it to behave semi-plastic. We get the wet weight of the soil, and then we put it in the oven and dry it up and get the dry weight of the soil and subtract the wet weight from the dry weight to find out how much moisture in the soil for it behaves semi-plastic. The difference between liquid and plastic limit moisture contents is called plasticity index, or PI. If your PI is less than 20, you got low swell potential. 20 and 30 is mildly expansive. 30 to 40 is highly expansive. Above 40 is very high. So places like Willis, you got, sandy soil, so it's got, low swell potential. Places like Texas City got fat clays, got PIs greater than 40, very highly expansive. A couple other tests we run is called hand penetrometer and a torr vane. Hand penetrometer, you take the soil sample, you push this thing in there. You can read what kind of strength you have here. Torr vane, you put it at the end of the sample, ensure the torsion, and read what kind of strength it has. And you also run unconfined compression test, where you put the sample in here, and this is a proving ring. It's deflection, you shear it, see how much load it can carry, the soil can carry. That's important for design of the excavation, for the pool. If you got any buildings out there on your rec center, for the foundations, so how much load it can carry. So this is the Willis site, boring logs from 0 to 4 feet. We had sand. Below that, they had lean clay with a PI of 22. Below 13 feet, we had fat clay. So that's not a bad site. It's got sandy soils, silty sand 0 to 6, 6 to 13 lean clay, 13 to 25 fat clay. PIs ranging, well, about 22 here. So their soils are really loose near the surface. The silty sands are loose. Um, Potential vertical rise. Whenever you do pools, you always check the PVR, potential vertical rise on that site. Potential vertical rise is expressed in inches. It estimates how much swell you're going to have on the site, how much heave you're going to experience for a specific location. In this site here, at the deep end of the pool, assume 6-foot pool depth. The PVR was less than half an inch. Shallow end, 3 feet deep, less than half an inch. Allowable pool movements is 0.5 inches. That's the allowable. Because after half an inch of pool movement, kids are playing around the pool, they can trip over and, hurt themselves. So we don't want the pool to be moving more than half an inch. Site number 1, we reviewed the specifications, plans and specifications. We did a site visit to check the bottom of the excavation of the pool. We ran the density test after compaction of the bottom of the pool. We checked the steel placement and we tested gunite. There's a typical pool construction here. Got 8-inch thick gunite, and you got steel in there. Soils are, sandy and lean clay, so there's no soil treatment required as long as the bottom is properly compacted. Gunite, in this case, is supposed to be designed for 4,000 psi. Construction, they start excavating the pool. They just get a backhoe or something else. They just start excavating. This is the bottom. Doing the construction. We also ran hand penetrometer tests at the bottom of the pool. That's a hand penetrometer, and push it into the soil, get a strength. We usually like to have a strength of at least 2.0 TSF. On the hand penetrometer, it was 2.7 TSF, so the soils at the bottom of the pool was strong. We also wanted to check the compaction of the soil underneath the pool, so we ran density tests. Here's a nuclear gauge. You poke a hole in the ground like that. You put your nuclear source in there, and it emits gamma ray, and you've got a receiver here. And if it receives a lot of gamma ray, that means the soils are not compacted good. If it's received less, there's compaction. There's correlations between the gamma ray and the receiver and the soil. So we run density tests. We check a proctor test on the bottom of the soil at the pool, what kind of a proctor it has. That's the relationship between density and moisture of the soil. The dry maximum density here was 113.8. Optimal moisture was 15. These are the compaction tests at the bottom of the pool. They ran it at 4 locations, and densities ran from 99.7 to 96%. Required compaction was 95% standard, so densities passed. Steel observations, we checked the steel placement for the bottom of the pool. They had these blocks in here. We told them to remove it and put plastic chairs. So we wanted the plastic chairs, not the blocks. We checked the steel placement, the size of the steel spacing. Make sure it meets project specifications. Then we check the gunite. Of course, gunite is a mortar or a concrete that's pneumatically projected onto a surface at high velocity. If it's mixed dry, it's called gunite, or it's wet mixed, pre-mixed, it's called shotcrete. It's a mixture of cement and aggregate. Aggregate size not greater than 0.75 inches in size. Do not apply if the above temperatures above 90 degrees, wet mix, and 100 degrees for dry method. That's gunite. Lower temperatures for steel surface below 100 degrees before shooting gunite. Gunite may be proceeded if the ambient temperature is 40 degrees and rising, 50 degrees for latex modified shotcrete. Do not start if the temperature is 40 degrees and falling. Concrete materials, shotcrete materials, temperature shall be should not be less than 50 degrees or higher than 90. Shotcrete should not be placed against frozen surfaces. These are some general stuff. That's the truck that kind of mixes the gunite out there. They got the cement and the aggregates. It's gunite, the truck there. See the material coming out. You got a hose, comes in, they start shooting it. You can see the shooting the gunite. Ideally, you want to shoot them at a 90-degree angle, not in 45, not a 45-degree angle. Here they're shooting the gunite. Gunite panel preparation. We want to test the gunite. So what we did was get a wood panel, 3 feet by 3 feet, 3 feet by 2 feet. ASM's got a standard on it. We shoot the gunite into it. Let it cure for 14 days. Gunite panels are equivalent to concrete cylinders used to evaluate compressive different than a concrete material. Because shotcrete cannot be shot into closed cylinder form, the shotcrete is shot into an open-faced form. Cores are taken from the panels and tested at appropriate age. Usually we test them at 14 days and 28 days. Sometimes if test them at 7 days. We go out there and core them, like 2-3 days after. No reinforcing should be in the panels. ASTM C1140 standard practice for preparing and testing specimen from shotcrete panels. Provides the testing requirements. The panels are samples of the shotcrete spread onto the site into a form under controlled conditions. Standard cores are later, of course, taken from the panels. Gunite panel coring. It's a coring machine. You go out there and start coring the panels. Typically, we core them after 14 days. Like we said, ASTM 114 talks about how to do these things. Test panels of shotcrete are spread into a form, and of course, they indicate how we go core them and take them to the lab. When we take them to the lab, we cut the ends of the core like that, so that they have nice and clean, ends, not jaggedy. So you cut them like this. You put them in a plastic bag, and you put them in the curing room for 5 days for the basic moisture conditioning to stabilize the moisture gradient throughout the cores. And then we test them after 5 days of curing. These are the cores. You measure them, you get the dimensions of them, and run densities on them. You cap them, and put them in a machine, and you break them. Concrete area represented by cores. I mean, that's how we determine if the cores passed. For like typically for 3 cores, the average core should not be below 85% design strength of 4,000, and not single core should drop below 75% of F''C. If it does, typically it fails, or you got to do additional testing. For 4,000 psi gunite, 75% F''C is 3,000, 85% F''C is 3,400. When we read the testing for 7 days, we got strengths of 3,600, 3,550 at 28 days. We got 380.88. So the gunite passes the strength. It's not 4,000, but it still passes. When you put the pool together and you shoot the gunite, you're supposed to go out there and cure it with moisture conditioning. Add water on the top of the surface, put burlap on it or something to kind of cure it for like at least really 14 days, maybe 28 days, even better. After about a year or so that for the pool was constructed, start having cracks in it. We talked about the cracks before, we showed it. We had to go out there and core that gunite that was actually placed out there, and we saw actually when we cored them, there were voids out there in the gunite. So we cored them at various locations. See the voids? Voids. We cut the ends of it, put them in the curing room for 5 days, measure the dimensions, cap them, and we broke them. The compression machine. We got test results of 1,600, 1,500, 1,600, 1,500. So it's supposed to be 4,000 psi, and they all failed. But most of the reason why it failed was a lot of voids in it, probably due to application of the gunite, the way they were applying it. They had voids in it, and the mix couldn't have developed the 4,000 psi, the strength that they're supposed to have. So they said that basically they're going to keep it going for the summer. We also did petrographic analysis of the gunite. We took a couple of cores. We took a slice of that gunite and put it on the microscope, and we saw a lot of voids in there. Basically, we had a petrographic guy looking at it, and he showed a bunch of voids in there in the gunite. And also, it showed a lot of black, oily stuff in there in the gunite. So what the petrographic said, high voids were present in the gunite, resulting in lower compressive strengths. So when you have a lot of voids in your gunite, you're going to get low strength. And one of the cores that we did the petrographic on had oily stuff in it. I don't know, they had some oil mixed in it or not, that caused problems with the gunite strength. And also, he thought that the gunite was not cured properly during the initial 14 to 28 days of curing, causing it to dehydrate and develop crazing or hairline cracks in the cores. Based on a review of the compressor test results and petrographic analysis, the gunite does not meet project specification of 4,000 psi. We recommend the entire pool be removed and replaced. And so what happens was they're gonna remove the pool at the end of this season, and put a new pool in there with a new gunite. So that's what happened to this one. Texas City site, you got gumbo clay soil in here. It's supposed to be really fat gumbo clay. They went out there and that's the pictures of the pool. We did the initial geotechnical study for it, field exploration, geotechnical recommendation, Chemical injection specification. We did quality control, reviewed the plans, chemical injection observations and post-injection testing. We did site visit to observe pool bottom excavation, density testing at the bottom of the pool, steel placement, gunite testing. We did geotechnical work for the pool, and that fat clay soils were present at the job site. Cut the end of it, put it in foil, put it in like a box like this, wax box. Check for root fibers. That tells us the depth of movement, active zone in expansive soils. This is like 6 to 8. That one is 4 to 6. Typically, movement active zone was 10 feet. That's the soil. Fat clay, fill 2 foot of it. Below that, you got fat clay. You got a PI of 64, PI of 57. The soil is 1,000 PSF. Not very strong, but that's good enough to build a pool in it. So 0 to 2 feet, we had fat clay, 225 fat clay. PIs 40 to 63, set 59 to 76. So we got highly expansive. We checked the PVR for the pool. At the deep end, we had 4-foot deep pool at 4.2 inches of movement. Shallow end, 6 inches deep pool, potential movement of 5.7 inches. Well, this is not acceptable. We don't want the pool to have movement more than half an inch. So we cannot have more than half an inch movement. We develop what's called chemical injection specifications. It says you got to go and inject chemical injections all the way to a depth of 10 feet. An average swell should not exceed 0.5%. So inject in the top 10 feet and not, well, actually 0.4%. So we reviewed the plans and specifications, observed chemical injection. We did geotechnical boring to make sure chemical injection was effective. We did site visit to observe pool bottom excavation, density testing at the bottom of the pool, steel placement, gunite sampling. The gunite, the mix design for it, it said 4,000 PSI gunite, 28 days. So these are kind of like specifications. They'll talk about the thickness of the concrete and on the walls and steel placement. Basically, it says follow the geotechnical report. Chemical injections. If your soils are highly expansive and you want to reduce the movement, you do chemical injection. This is a clay plate that's got negative charge on it. Water, it's got positive charge. So it wants to absorb water. As it does, it expands. It moves up. So what we do is reduce the negative charge, and so it doesn't absorb as much water, so it will not expand. Basically, it's called cation exchange. Just in soil that removes the mono valent cations like sodium and potassium, replace them with divalent cations with like calcium. This is the tank, the chemicals are in it. They go in there and start pumping them into the soil. This is the device that, basically got these pipes. They're like 2 foot apart. They inject them all the way to a depth of 10 feet, the chemicals. After the injection, we go out there and, of course, get sample of the soil and run swell tests. We put soil sample here and put a load on it here and see how much it's going to swell. These are the swell test results, and you can see in here 0.23%. Here's another swell test. This is time. This is percent swell. This one swelled 0.28%, all or less than 0.4% or 0.5%. Here's 0.35% swell with time. Here's the swell, 0.53%. Here's 0.28%, 0.53%. The average should not exceed 0.5% or 0.4%. And Construction, pool excavation. After the chemical injection, went out there and passed the chemical injection. They start excavating the pool. We check the pool bottom, starts raining, got wet, so they start pumping the water out, and they put a bunch of lime in it, dry it up. Do a hand penetrometer test to make sure the bottom wasn't strong. And the hand penetrometer test showed 2.5 TSF, which means the strength bottom of the pool is good. We also ran density tests with nuclear gauge. See the clay is cracked up. Gonna dry it up. This is the Proctor curve, show optimum maximum dry density of 91, optimal moisture content 28. We run 6 density tests, and they ran anywhere from 99 to 99.9. So now the bottom of the pool nice and hard, density's passed. Then they started placing the steel. We checked the steel spacing and placement. Again, we tell them to use plastic chairs. They brought in the gunite, it's supposed to be 4,000 PSI. It's gunite truck. Start pumping the gunite. Again, that's dry cement and aggregate. They add water to it at the nozzle over here. So they shoot it on the ground. Becomes gunite. So they add water here. See the valve here? They add water to the cement and aggregate. Gunite panel testing. That's a typical panel. Start shooting the gunite into it. That's the panel. You let it sit there. Typically, we core it after 14 days or maybe 2 days. Just depends when we need the test results. We start coring it. These are the cores. So we cut the ends of them, make nice, put it in curing room, let it cure for 5 days, measure the dimensions, cap them, you break them. At 7-day tests, we got these numbers. Everything failed. It's supposed to be 4,000 PSI at 28 days. So at 7 days, I'm looking at about, a lot more than this values. 70% of that that's 2,800 PSI. None of these are close to 2,800 PSI. We kept the course for 28 days. These are the cores. We break them at 28 days. The strings are 1,600, 1,200, 1,100, 831. All of them fail. Since the core failed, we decided to go to in situ coring. So we went out there and cored the actual pool. So we did GPR before coring with ground penetrating radar. Ground penetrating radar uses an antenna that transmits electromagnetic energy like a cell phone. There's a receiver and an antenna that receives the reflected signal. So the GPR, we try and do it, make sure we don't hit any steel. So we run it, and we find places that there's no steel in the gunite. That's the GPR machine. And we'll start coring it at those locations. These are the cores. So core out there on the side too. We see voids in the gunite. Again, voids in the gunite. These are the cores. We cut the ends. Cure them for 5 days. Measure the dimensions. Cap them. Break them. The core's breaking. The strengths range from 2,000, 1,500, 3,400, 2,400, 3,200. These are in situ cores from the pool. All failed. So we did the review of the pool design. We do chemical injection monitoring. We swimming pool excavation observation, swimming pool steel placement, gunite testing of the cores of the panels failed. Gunite cores from the pool, actual pool failed. So that's a problem. Based on review of the compressive test results, it's our opinion that the gunite does not meet pool project specification. Entire pool should be removed, or area should be recompacted, and we need to go ahead and install a new pool. The new pool, we need to wet cure it for at least 14 days, maybe 28 days, make sure it gets cured properly. It is vital to the overall strength of the gunite for it to cure properly. So that's it. We had 2 sites with bad gunite. And so if you all see pictures of the pools with a bunch of cracks, send them to me. I use them for presentations. Pictures of anything interesting. Program evaluation. We got a poll in here. We're gonna put a poll together. See what you all think of the program. This program is going to be on YouTube. You're going to get 1 hour PDH on it. If you need to reach me, this is my contact information. DE at geotecheng.com and 713-699-4000. We're going to have a bunch of new webinars, so you're going to get notices. You're going to get within a week or so your PDH for 1 hour. Questions?